Hi, I'm Pelin from Chemistry Department. Today I'm going to study simple harmonic motion on a spring in a vertical setup. Objective. In this experiment, simple harmonic motion is going to be studied by inspecting the oscillations of different weighted blocks that are attached to a spring in a vertical setup. Theory. The distinct shape and form of a spring enables it to turn to its initial state after getting stretched. How far the spring will be stretched from its equilibrium point is dependent on the force that is applied to it and the force constant that is unique to each spring. Hooke's law states this as: stretching the spring will insert energy into the system. The spring will then start to oscillate back and forth due to the law of energy conservation. The period is the time passed during each oscillation and is expressed as. Hence, if one knows the exact force applied to a spring and measures the change in its length, the force constant can be calculated. This value, along with the mass, can then be inserted into the latter equation to find the period of the motion. Equipments: balance, ruler, timer, calculator, durable spring which is also not very stiff, attachable blocks to use as weight, stable and long hanger to attach the spring to. Procedure. The weights of the blocks are first going to be measured with the balance. They will then be attached to the spring one by one, and the elongation of the spring each time will be measured with a ruler. The force constant of the spring can then be calculated. Using different amount of weight, this procedure is going to be repeated a couple of times, and the values will then be put in a table. The period of motion will be manually measured with a timer by carefully observing the oscillations of the spring. If the oscillations turn out to be very fast, and the time between each up and down motion is very short that it is hard to measure accurately, we might also measure the time passed between every 5 or 10 ups and downs, for the sake of improved accuracy. The period will then be the division of measured time by the number of ups and downs of the spring. Measurements will be carried out 10 times each. The period of motion can also be calculated integrating the previously obtained k values and the mass values of the objects into the equation introduced in theory. The calculated values and the manually measured values of the period for each mass will then be tabled, and the error percentage will be calculated. Here you can see the data tables. Conclusion. The oscillations of a spring are not random and have a fixed period if the mass that is attached to it is also fixed. When calculating the period, the mass of the spring itself can be neglected, since the geometric and massive properties of the spring that contribute to motion are taken care of by the spring constant. In this experiment, constant is measured to be 11.532, which is the slope of the trend line of the force and strength length graph. The period of motion is proportional with the mass that is attached to it and inversely proportional to the spring constant k. It can be concluded from these graphs that if k constant and masses are measured properly, the period can be determined with great precision. To improve the accuracy of measurements, it is advisable to fix the spring to the hanger with a tape to prevent the spring from jumping up and down on the stick and completely lose contact with the hanger at times. To tape the masses at the lower end of the spring would also be wise for the same reason. Doing this should also minimize concerns regarding friction in the setup. Lastly, choosing appropriate masses for the kind of spring that will be used is also vital. If the spring is very stiff or it has very little resistance to force, data measurement will be very hard, and in some cases impossible. Determining the spring constant beforehand can give us a good idea about the properties of the spring and what kind of masses would be the best choice to observe oscillations.